Well, hi there. Thanks so much for showing up your math learning. It's Mr. Jennings, and we are looking at graphing tangent and reciprocal trigonometric functions. So, one of the things that you'll recall from Unit 2, if we had something like 1 over x squared minus 3x minus 10, you would have factored that denominator just like as a force of habit, x minus 5 times x plus 2. And then you would have said, well, I know that this thing's going to have vertical asymptotes, right? Because we clearly cannot have the denominator equals 0, so we can't have x be 5, nor can it be minus 2. So then you would have proudly just shown your asymptotes like so, just showing them to the world that way, and then graphing the function something like that. I don't know. Who can be bothered figuring that out right now? But you remember that skill. Okay? We're going to be using the same skill today when we're graphing these reciprocal trigonometric functions. This exact same logic applies. So because we have things like cosecant is 1 over sine theta, if you're graphing cosecant, or if you're thinking about the domain of cosecant theta, we can't have sine theta equals 0. Okay, that's not allowed. That's excluded from the domain, which is to say theta cannot equal 0, pi, 2 pi, dot, dot, dot. Right? Can't be those things. That's where you're going to get asymptotes with cosecant. Secant has different asymptotes because you see it's got this cosine down there, and tangent. And, well, let's talk about tangent in a second, because, I mean, this is not the efficient way I'd have you thinking about tangent. Since tangent itself is undefined at times where cosine is 0. Sine theta over cos theta. Okay, so this is another way of writing tangent. We know this identity, the tangent identity. And if cosine theta equaled 0, then it would be undefined. So that is to say, for tangent, you're going to get your vertical asymptotes at pi by 2, where cosine is 0, 3 pi by 2, and dot, 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 5 pi by 2, etc. Okay, so looking at cosecant, I mean, we get the pretty clear picture here. There's sine, we already talked about that. This is where f of x is undefined for cosecant of x. But if we were to look at pi on 2, okay, that's where sine is at its maximum. Cosecant of x, it's also it's at its like kind of local minimum here, because 1 over 1 is just a fancy way of saying 1. Here we're undefined again, and no surprise, any multiple of pi is going to be undefined, because, and you can think about your functions as well, anywhere where sine is hitting the x-axis is undefined when we reciprocalize it. Okay, and then this one here, this is where cosecant reaches its local minimum. Sorry, that's the local maximum. I think I misnamed them. We'll see them when we sketch them. Okay, like that. So let's keep going. All right, the secant, on the other hand, has to do with cosine, and the places where cosine is equal to 0. Of course, you can think about your unit circle, and there's one of them. Cosine is 0. And there's another one. And wouldn't you know it, I could just keep on adding pi to this. Every time I do a 180, that's adding pi. And all of those are undefined for secant. So we have our vertical asymptotes here and here. And of course, you can imagine your cosine graph, which starts at a maximum, hits fall, goes through winter, hits spring, and comes back up, and there's where your asymptotes would be. You visualize that, and then imagine your asymptotes. Okay, and then this one here, this is 1, and this one is minus 1, and this one is 1. So we'll take a look at some examples. And then, when you're thinking about tan, of course, cosine gives you your vertical asymptotes. Cotan, sine gives you your vertical asymptotes. We're always getting asymptotes from the denominators of our rational functions. And all of these qualify as rational functions. They apply this exact same logic as we've seen with polynomial rational functions. Let's go. So tangent, if we are like some interesting points on tangent, okay, sine over cos. So this one here, this is where tangent is at 0. Okay, so when sine is 0, even though that's in the numerator, that's still giving us useful information. That's showing us one of the zeros of that function. This is one of its x-intercepts. We have another one over here. We have another one over here, just underneath my face there. But then these ones is where we get our vertical asymptotes. Okay, anytime the denominator is 0, that's where we have a vertical asymptote. So we'd have them at those places where tangent is undefined. And cotangent, it's just flip the script, okay? It's just flip all that entire logic. We're going to put cosine on the top. 1 over 0, my friends, is vertical asymptote. 0 over 1 or 0 over negative 1 are fancy ways of saying 0, and we have our x-intercepts. And then this one is also a vertical asymptote, and this is a vertical asymptote. There's one other thing I want to talk about with tangent and cotangent is that there's another convenient point that we can look at for both, and those are your pi by 4s. Okay, your pi by 4 is a nice point, as well as your negative pi by 4s, and your 3 pi by 4 and 5 pi by 4. These are the places where the function is equal to 1 or negative 1. And those are nice points to highlight because you can use them to show various transformations really clearly. You can use it to show stretches, shifts, like c-value shifts and things. So it's a nice one. Consider including those in your tables. Okay, so let's sketch this one on the domain 0 to pi. So we're going to prepare our y-axis and our x-axis here. Okay, we're noticing that we're going to be stretched by 2 and minus 1, so things are going to happen. But when you're sketching one of these reciprocal trigonometric functions, start with this piece first, then stretch it, then shift it. Okay, do those later. So my first step is actually going to be to consider like g of x, which is kind of the reciprocal of this, and that's equal to sine of 2x. And I'm going to be interested in sine of 2x. Again, I'm ignoring this piece, I'm ignoring that piece for now, because we're going to stretch it later after we do the reciprocal. So sine of 2x, and we want this on the domain 0 to pi. So I happen to know that my period there is equal to 2 pi on k, which in this case is 2, so the period is pi. So I'm going to get 2 full cycles here, which is just great. It's exactly the number of cycles I wanted to see of this thing. So there's pi, there's 2 pi. Okay, great. Now, sine 2x, okay, it starts in the spring, and we get our quarter periods here. So our 1 quarter period is equal to 4 pi on 4. So I'm just going to mark those here. Doop, doop, doop. This is pi by 2, and I don't want to mark the little ones, but I'm just going to, like the quarters, but I'm just going to put a little tick there. Anyone who sees that is going to know what that means, because it's just going to get too busy otherwise. Okay, so we know that this one starts in spring, goes up to a maximum there, comes back to fall, comes down to a minimum there, and then comes back, and that's its period. Okay, so it looks something like this. All right, and I do this just ever so gently. I really don't want to like make it obscure what my stretched one is going to look like. Okay, so there's my sine function that's underlying this reciprocal trigonometric function. So now I get out my asymptote pen, and I'm proudly going to put on my asymptotes. Okay, so they are wherever this thing has a 0. One of you was asking, do you have to show an asymptote here? Yeah, you can. I mean, you can. Yeah, it's going to be hard to see right on the axis. So long as you show asymptotic behavior there, your sketch will be fine. Okay, So now, when we get interested in this one up here, all right? So we're now turning back to f of x is equal to 2 cosecant of 2x minus 1. We might see what is up with my handwriting today. Whew, it gets a little bit sunny and it really goes out the window. So I might be thinking about like my general function a little bit first. I'm thinking like these points here, that's like 1 in cosecant, and then it sort of goes up this way and this way towards the asymptotes, and it's very symmetrical on both sides, not like what I'm drawing. That's what I drew is pretty good. And then this one here, -1 is reciprocal as -1, but then it goes down towards the asymptote that way, and down towards the asymptote that way, and so on. I mean, these are all the same. I'm just going to do the 2 for now. But then I want to stretch it by 2, and then lower everything by 1. So what's going to happen there is we'll go back to blue. Okay, so I'm going to stretch it. So that's going to mean this one that's at 1 goes up to 2, and then lower it by 1. So it goes back down to 1, and it's there, but it's now more stretchy, so that it's actually like on top of this one, like that, and on top of this one like this. Okay, so it actually rises even faster because it's stretched by 2. This one, on the other hand, gets stretched by 2, so it will come down to -2. Just multiply that y value by 2, and then go down by -1. So it's actually down here at -3, like that, and it's way more stretchy than that one up there. So it looks like this. Same as this one over here. I know it's gonna be the same in this part of for the next cycle of this function. It's gonna look like that. And this one, it's going to be the same as this one. So I just push it forward a period like this. Are they parabolas? No, they're a different shape. They're like that, and they go very vertical when they approach their asymptotes. And that would be what my sketch would look like. If I really wanted to label some points, I might label these ones, and I might say this is the point pi by 4, 1, and this is the point 3 pi by 4, sorry, 5 pi by 4, 1, okay? And then this one down here is the point 3 pi by 4, -3, and this one 3 pi by 4, -3. It's not 3 pi by 4. It is the same, but it's 7 pi by 4. Aren't fractions fun, everyone? Okay, so there's a high quality sketch of that one. And I guess you know what's coming next. We're going to open up some Desmos. And we're going to type in cosecant, 2 cosecant of 2x minus 1. And then we check some of these points. Hey, pi by 4, 1. 3 pi by 4 minus, hey, look at that. But this one's 7 pi by 4 minus 3, yay. So we check it. And we see that they're not exactly parabolas, right? And then if for style points, we're going to flip this into a pi by 2 scale, turn off the minor grid lines, and you can see that like that actually kind of is our asymptotes, right? Okay, cool. Let's keep going. So that's that example. What about this one? This one where we have a phase shift. Oh my. Okay, well this one here is very tricky. Okay, so first thing I would want to do is factor that because it's designed to mislead us. So we would have 3 bracket x minus pi by 3, and we just recall that that's something we have to do to see the D transformation correctly. So we're going to be secant, but shifted by pi by 3. Now, I'm going to look at like a different function that I can take the reciprocal of. G of x is equal to cosine of 3x minus pi by 3. Okay, and I'm just going to look at that. I'm going to sketch it and then get my asymptotes, find out where that's equal to 0, and so on. And then, what else am I going to do? Right, yeah, get the asymptotes, get those points that are like the, whose reciprocal is themselves, where this function kisses its reciprocal, and then transform those points. So, sketch the axes. So we're going to be here. We're more interested in the positive side, so we have this. We want this on 2 pi, but we see that our period is 2 pi on k, which is on 3, equals the period. And the quarter period is pi on 6. I get that by multiplying the period by a quarter. And, right? So you go ahead. You're working away on this as I'm working on it, I hope. This is not learn-tertainment. This is you're active and doing. Otherwise, my pacing is really leaving something to be desired. Okay, so now we have the period is 2 pi by 3. So we're going to just mark our pi by 3s as well. That's going to be really useful, right? We don't need to mark our pi by 6s because they're going to be halfway in between each one. So this is pi by 3. It's 2 pi by 3. That's 1 period. And then this is 4 pi by 3. That's 2 periods. And then this is 5 pi by 3. And our quarter periods are the sixths, pi by 6, and they're in between each one. Not going to mark that. So if I were to graph cosine, cosine starts at the top and goes down. So I know that if this is like 1 and the minus 1, then we are going to have here. We'd normally start there and go down, right? And then, we have the quarter period, so the quarter period is halfway. So we would be up here, and then down here, and then up here. That's a really long 2/3. So there's like 1 period, and it would look like this. But then we shift it. We shifted all pi by 3 to the right. Okay, so if I go back pi by 3, I'm going to be starting at a minimum, aren't I? That's going to be negative pi by 3, because that's 1/2. That would be there, negative pi by 3. So that's 1/2 of the period going back. And now I shift everything to the right. So here. This is our cosine function that would now start there. And it hits a maximum here and a minimum. 2 pi by 3 is its period. And my scale is really wigging me out because it really stretches there, doesn't it? And then up and down and up and down. Okay, so that is the underlying cosine function, where the d transformation has been applied and the k transformation has been applied. Okay? So that's the thing that we're going to take the reciprocal of over here. And then we're going to add 2 to it. That's the only change that we're going to make, is we're going to add 2. So let's go ahead and choose a color that we're going to do this one with. So secant, we're going to have our, let's get out our asymptote pen first. We'll put our asymptotes proudly where they belong, at pi by 6. This one is pi by 2, and then this one is 5 pi by 6, and then this one is 7 pi by 6, and then this one is 3 pi by 2, and this one is 11 pi by 6. This is where our asymptotes go. Okay, so we just get our asymptotes on. And then we consider what happens when we take the reciprocal of this function. So 1 goes to 1, and it goes up, but then I raise it up by 2. So that's up here at 3, and it goes up towards the asymptotes on both sides. This one here at minus 1 flips onto itself, but then we raise it up by 1, so it's actually here and going down. And we weren't asked to graph that side, but we're going to, just for completeness sake. Okay, and same, now I just progress things along the period. So this one is up there, and it goes down, and it goes down. This one is up in the sky, lifting its arms up high, saying, "Wee!" It's important that you personalize your functions a little bit to have more fun. Last one, so this point here. Wee. And then, of course, we're going to pop back into Desmos. We're going to change this to secant. And we aren't 2, we're just secant 3. We put this in brackets because we were 3x minus pi plus 2. I think that's what we had, right? Did I label any points? Pi by 3. So let's see. Yeah, it's pi 3. Yeah, that's the same. So that's how we do. Okay. So again, main idea is when you got this one, consider the function that you're taking the reciprocal of, which includes the whole argument of the trigonometric function, the k value and the d value, properly factorized. Visualize it, get your asymptotes, take its reciprocal, and then apply the amplitude and the c transformation, changing the axis. Okay, sketching tan. All right, I'm just really excited to sketch tan here. So tan, we're going to go pure like that. We're going to sketch it on 2 pi. So there's 2 pi. I'll try and do a better scale this time. Here is pi. Our scale hasn't been changed at all, so we are going to put on pi by 2 and 3 pi by 2. And then I'm going to show the quarter pies just with some ticks, but not with a label. And that looks better than I've been doing, so I'm super pleased. Okay, so now I would also recommend just going back to this grade 11 skill of just taking some useful x values and some values for your main function. And then we're going to keep our x values the same. Neither this nor this is changing any x values, but we are going to do 2 tan x minus 3 there. We're going to multiply by 2 and subtract 3 to all the values we get. So when x is 0, tan x is 0, and there 2 tan x minus 3 is just going to be minus 3. When x is pi by 4, okay, tan x is 1, so this will be 2 times 1 minus 3 equals minus 1. And then pi by 2, tan x is undefined, so we have a vertical asymptote, yo. Just so excited to show this vertical asymptote. Alright, just so very, very thrilled. And then I also have another one over here. So I'm just going to show my asymptotes to my viewers. Okay, and then maybe I also consider 3 pi by 4, which for those of you following along at home is this angle, where we have CAST. Tan is negative because only sine is positive over there. This is negative 1. So this is going to be 2 times negative 1. Oops, which is minus 2. That's why my brain does that. Minus 3 equals minus 5. Fix it for the viewers at home. Okay, so we're going to do this, and then we pretty much, the period of tan is actually pi, because it repeats itself. This totally repeats the same pattern over here, because it alternates between positive, negative, positive, negative. And so it's not like sine and cosine that have a period of 2 pi. Tan's period is pi, which is fun. So actually, unless I put in pi here, we have tan x is 0, and that will mean we are at -3. Okay, now I just go ahead and put these points on there. So we've got 0, -3, boop. Okay, there's a point 0, -3. We've got pi by 4, -1, so we are up here. Pi on 2, this is an asymptote, so we are like whoop, going to approach our asymptote. And then 3 pi by 4 is a -5, so we're down here, sort of swinging up past the asymptote, and then at pi we are at -3. And so we're like swinging down towards the asymptote that way. And then this one, just translate that forward by the period. And then this is our oh so beautiful picture of tan. There, done. And then you check it in Desmos and find out that I'm good at this now. So yeah, this is correct. So go ahead and practice. This is what you now do, okay? If you've been following along and you've practiced with these examples, you're already in pretty good shape. Now see if you can do it without me in your ear saying, next is this, next is that, next is the other thing. And guess what you do if you have problems when you practice? You come find me, okay? You ask me in class. You ask me by an email. You put it in the YouTube chats to drive up my viewer engagement. No, that's not something I care about. I care about your learning. So you showed up for your learning to get to this point. Now take that one extra step and find something that's tricky inside this work that's available to you, and get her to go. Get a good question out of that, and I'll be delighted to help you with it. Bye for now, everyone.